All right, so like I was saying last time, we're going to just use our regular numbers. We're not going to use hexadecimal right now. And as a warning, Python, if you really go and open the hood and look under, it's not going to work exactly like this, but it's going to act like it's working like this, because this is how things work traditionally. And another thing to note too, so there are some things that are just true. For example, a linear search, the algorithm linear search. If you follow, it's like, if I ask you, well, if you do a linear search and you're guaranteed to like find the thing you're looking for if it's there, can you like prove it to me? And you're going to go like, I mean, if it's there, it's there. Like, it's almost hard because it's so obvious, right? Like, it's just, it is what it is. That's just the way it is. If you follow these steps, you'll find it if it's there. It's like something that's just true within our existence. But when we're talking about like this stuff, there were a series of design decisions made. They weren't arbitrary. They made sense. There was a reason why these things happened. And if you pay attention to why things were done a certain way, everything's going to make perfect sense. If you don't pay attention, you might get mad about how this is going to work. But if you're paying attention, everything will make sense. And the root of all this comes down to what's being stored in memory. All right, so here's an idealized view of memory inside a computer. I'm starting at some arbitrary number. I started at memory address 124. It starts at 0. It goes on to like a bajillion, right? Ideally, it goes on forever. So this is like RAM, right? And I've got memory addresses, and it goes on forever, okay? So if I say, what's at memory address 126? Well, it's a C. Why? Well, just in my little picture here, I put contents there, content there, because like whatever, all right? It's like a list, kind of. You can index memory effectively, okay? So that's what we've got going on. We've got memory. Memory has memory addresses and content associated with those memory addresses. Now here I'm representing like, oh, there's C for content. Now, of course, there's not literally a letter C in there. There's some zeros and ones that would get decoded to it. But for our purposes, we're thinking of it as the letter C. The letter C fits nicely in there. Great. Any questions so far? This is a topic that it's really important that you pay attention to, because it's a good one, but it could throw you off if you're not paying attention. And by the way, this is one of my favorite things to teach in this class, in this semester, 161. So primitive types are things like your integers, your floats, your booleans, an individual character. They are called primitive types. So let's say we have a single integer called x. An integer is a primitive type. In many programming languages, integers take up 32 bits. So we have 32 zeros and ones that we can use to represent an integer. So there's an example. 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0. That is a 32-bit number. That is a number. Well, actually, no. That's a 32-bit pattern. And if we decode that pattern as an integer, it's the integer 709,582,100. Why? Because it is. That's just, it is what it is. So that pattern, that binary pattern, can get decoded to that integer. All right? So since we know how much memory, we need 32 bits. We know how much space. A bit requires some physical space to store. We know how much room it needs. So if we have 32 of those, we can break memory down in these 32-bit chunks really nicely. And I could shove an integer in that chunk, and it's going to fit perfectly. It's great. Yeah, we can put them nicely and divvy up chunks of memory. If we divide memory into blocks of 32 bits, we can create an integer variable like x equals 17. So I've got the integer, it's a variable x, storing the value 17. The value 17, whatever binary pattern it is that's represented by 32 bits, will be shoved into that memory address. So I know I showed in the example above the letter C in there, but really there would be 32 bits in this chunk of RAM. So if I were to say, okay, x is 17, well, the value 17 has to go and be stored somewhere in RAM. So your computer is going to say, I need some RAM. There it is. And for our purposes, it's entirely random and arbitrary how, not random, but it's not important to us how your computer decided memory address 126. All that matters is that your computer said, okay, we can put it here, memory address 126. It's free. I can put the number 17 in there. And your computer will know, Python will know that, oh, well, that variable x, when I want to know what's in x, I go to memory address 126. And there we go. We have the value 17 in there. That's how it's going to work. Okay? That's it. It's like bookkeeping. It's just, imagine I have a ledger, and I just go, okay, at line 126, I put the number 17. If you ask, like, okay, what's x? Well, x, well, that was, let's go check it, right? That's all that's going on. Okay, it's bookkeeping. Any questions so far? Along the way, if you have any questions, ask when the questions come up. Don't wait for later. Ask when it comes up, because otherwise it'll be too late. If you want to make a copy of the value x, something like y equals x, well, what happens? Well, we copy the, listen very carefully to what I'm saying. We copy the contents from the location with the label x, place the copied value in another 32-bit section of memory. How we select that other section doesn't really matter to us. And then create a label y for that copied value's location. So we go to the memory location. The contents of x are copied to y. We go to x. Well, x is 126. What's in 126? The number 17. Really, it's 32 zeros and ones, but it's the number 17. We find another memory address, 129. Entirely arbitrary, not important how it's picked. And we give that the label y. Great. So we went to the memory address, and we copied what was stored in that memory address at that location, the number 17. The number 17 was copied, right? Even though I haven't shown this to you, I'm willing to bet that so far you're like, yeah. Oh, this basically is how I assumed it would work, right? So far so good? Yeah? Happy, sad, questions, thoughts, anything? Yeah?
Does it stay in 126 as well?
Yes. The value of x, it stays there. It stays there. Yes. It stays unchanged. And the copy, it's just copied, and we get another copy of it. Yes.
32 bits, is that like a thing just for images that has to be?
It's complicated. For our purposes, right? Okay. Because I don't want people starting to listen to what I'm about to say to answer you. I'm very cautious about saying it. It really depends on the type, and things will be all different depending on the type and everything. It can't, well, and especially in Python, things will be a little bit different. There's 1,000,000,001 asterisks, but let's say traditionally speaking, no, it's 32, that's it. Everything fits in this nice 32-bit chunk, okay? Why? Don't worry about it. Someone somewhere said 32 is a good number, and we went with it. So this strategy works great for the types that have a nice defined size. An individual character can fit those 32 bits nicely. It can sit in one of these seats, right? This is a 32-bit seat. A Boolean, perfect. We can sit it over there. Now you might, so to your question, how many bits do you really need to store a Boolean? 1. Really, only 1, right? But let's not worry about that. Let's pretend we shove it in a 32-bit chunk. It sits nicely. A float can sit nicely. All these things have nice, well-defined sizes. But what happens if we don't know, like, look. Let's say I'm a computer program, and the first line of that program is, like, give me an integer. And you type in the number 17, and it gets parsed as an integer. And it's stored into the variable, the input. So someone enters the number 17. Now, before I hit run, before the program actually starts executing, the computer can know, oh, I'm going to read an integer. It's going to be an integer. It's going to get parsed as an integer. And I know how much room an integer is going to be. Before the program even runs, it knows how much room it needs to store that integer. right? It doesn't need to run to go, uh-oh, an integer, how big is it? It knows. But if I instead said, give me some arbitrary string, the computer goes, oh shit, how big is that? I don't know how big it is. At runtime, they might enter the string hello. They might enter the string I. They might enter the string today was a cool day and it rained a little bit and I felt a little bit and so on and so on and so. It could be a really, 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 really long string. So the computer has no idea how much room it needs to set aside for that string before it hits run. The integer, it doesn't give a shit. It's an integer. It sits in its seat. A Boolean, it sits in its seat. A string, ooh. How many seats am I going to need for all the letters that I'm about to get? I might get one letter. I might get none letters. I might get a billion letters. I don't know. What do I do? So here's what we do. Well, here, let me re-emphasize what I just said a little bit. So I was just talking about strings. I'm going to talk about lists. We can treat them as the same idea. It's a collection of something that could be arbitrary length. So above is a list with length 8. The letters A through H. But these are arbitrary labels that we can think of anything. Here they're like letters, but they don't have to be letters. They could be Booleans. They could be floats. They could be other lists. I don't care. It's just some list. Memory was divided into chunks of 32 bits, which is perfect for integers. But unfortunately, we need to store a whole list that contains integers, which is a total of 256 bits. And that's only because this is a list of length 8. It could have been a list of 8 length 80 or 800. It could have been a lot bigger. We don't know. It needs a lot more room, and we can't shove all those bits into one seat that can only fit 32 bits. There's literally, and I know it's kind of funny to think, but there's literally a physical limitation here, right? I know these things are tiny, tiny, tiny microscopic transistors on your computers, but there's literally physical locations. There's physically no room for them. So fortunately, we have a solution. Store each element within the list in its own memory location, similar to how we stored the number 17. So what we do is we section off a chunk of RAM. Section off a large chunk of memory for the list to hold references to each of the elements of the list. For simplicity, instead of storing references with For simplicity, listen to what I'm about to say. For simplicity, we're just going to find a chunk of RAM where we could put each letter. Each A, B, C, D, E, F, G, H. Remember, A, B, C, D, E, F, G, H don't need to be letters. They could be whatever. They're just some arbitrary label. So what I do, I go, okay, here's my list. It starts at memory address 677, and then the next one I put like B, then C, then D, E, F, G, H. That's my list. My list is in memory addresses 677 to 684. That's the list. I can't fit a whole list in one memory address, but I can fit the whole list in a chunk of memory addresses. So that's what I'm going to do. So yeah, just put each thing into its own memory location. Easy peasy. We're going to keep track of the fact that our list starts at memory address 677 and goes to 684. The trick is how this is going to be managed. This is where the idea of references come up. And if you have experience with C and C++, this is going to be similar-ish to pointers. And if you're experienced with C and C++, references are not references. I know. It's a whole thing. They're more like dereferenced pointers. So here we go. Here's that list. A, B, C, D, E, F, G, H. But I say like Z equals A, B, C, D, E, F, G, H. Okay? Each element of the list fits nicely into its own divvied up section. Really nice. It fits in its own seats. I have A, B, C, D, E, F, G, H. They fit perfectly. It's great. The information we need to find where that list is stored and other information about that list is going to be stored in the memory address that we label with Z. The list is not stored in Z. When I say Z equals A, B, C, D, F, G, H, you might be tempted to say, oh, store the list in Z. No, that's never happened. We store the list somewhere, but what's actually stored in Z is what we call a reference. I'll show you with a picture. This is what happens. So our list, that the computer said, oh, we can put the list right there. Why there? Don't worry about it. It doesn't matter. The computer decided it for you. You don't have control over that. At least not with Python. So there's the actual list. It's over there. What I'm storing in Z is a reference to that list. So if I ask you, what is the type of the thing in X? Well, it's the integer 17. In Y, it's the integer 17. Z, well, it's a reference to a list. You have a question?
Does the computer know that that is a list?
It depends on the programming language. And it depends on a lot of things. So Python, to answer your question, really it's not just a reference. There's going to be a lot of other stuff stored alongside with Z, along with the reference. But in some other languages, it's really just going to be like, here's the start of the list. So it really depends. Yeah. So Z does not store a list. It stores the information that can get me to the list. That's it. That's what it is. All right? Why? Because I can't fit a whole goddamn list in one memory address. I can't. There's like a necessity for coming up with a solution like this to address the issue of like lists, when you want a collection of lots of information. So unlike a primitive type, primitive types, their value gets stored, boom, right in their memory addresses. But when you have something like a list, it can't fit in a memory address, so we have references. And all of the new types and things we're going to be doing from now on are going to be stored via references. So get used to it. Okay, take a moment, look at the image, and see if you can explain why I've talked about this before, but why do we start counting at 0? Well, it's an offset. If I say Z, like we all know that what's at index 0 of Z? Well, that would be based on this, it's A, right? We've got A. Because it means go to the start and take 0 steps. Traditionally, you would be doing like arithmetic based on the memory addresses. You would say, go to this memory address plus 0. So go to memory address 677 plus 0. Well, that's memory address 677. 677 plus 1. Well, that's 678. And so on. Any questions about this? Ask now before I continue. Yes?
So like the stuff in the list can be like anything from like integers to booleans to strings, right? But you said that, didn't you say that strings can't fit nicely?
Yeah, so what do you think would actually be stored? Let's say D is a whole string. What do you think would actually be stored in D? Another reference to a string stored somewhere else. So actually, really, in Python, this was that thing where I said for simplicity. In reality, what's happening is 677 wouldn't actually be storing A. It would be another reference to A, which is stored somewhere else. Because it's a whole thing. But that's Python. That's Python. Traditionally, and in fact, Python goes out of its way to pretend that it doesn't do it like that. It pretends that it does it this way. Because this aligns with how things have been gone. Like this aligns with the design and convention. Yeah. All right. Now, If you haven't been paying attention, pay very special attention now. If we want to make a copy of z, like we did with the integers x and y, we could write something like w equals z. But what is z really? A reference. So when I said w equals z, I make a copy of the contents of z. But what's the contents of z? It's a reference. It's not a list. And just like with the integer, so this is where people are like, so it acts differently? No, it acts the exact same way. It goes to the memory address associated with that variable, makes a copy of the contents of that memory address, and puts it somewhere else. If you don't believe me, look, I even put it in bold somewhere. The contents of x are copied to y. Right? This is where I was like, listen, copy the contents from the address, from the location with the label x. We go to where that is. So if we go back down here, we copy the contents of the memory location of z and put it into a new location labeled with w. Just like that. The list was never copied. The reference to the list was copied. And if you're saying, but why? Because the contents of z were copied. And what's the contents of z? It's the reference. It's the address, 677. That's what it is. It only ever copied the reference. This does not alter the okay, yeah. So, if I were to go and make a change to w, and I go and I say something like w at location 4 equals p, the computer goes to the list referenced by w and alters the value at index 4. W, 677, 0, 1, 2, 3, 4. It becomes a p. But if I go and I look at z, well, z was changed. But not really. Z was left alone. It's just a reference. The list that Z references was changed. Why? Because we had two variables that were storing references to the exact same one list. This is called an alias. And there's nothing wrong with aliases unless you expect w equals z to make a copy of the list. But it doesn't because the list is not stored in z. So if I go here, let's do a new notebook. I'm just going to convince you. Right? There we go. Cool. I'm kind of recreating what we just did. I created a list of the characters A, B, C, D, F, G, H. I said W equals Z, which made a copy of the reference, not the list. So I said W at location P, or 4 become P. Well, it changes for both lists. But really, I just misspoke because there's no both lists. There's only one list. There's only one list ever created here. I have two references to the list. One's labeled Z, one's labeled W. And when I change that one list through one of the references, it changes the one list. Any questions about any of this? Here, give me a sec. I want to try something really quick. So Python, there's a bunch of information that's stored along with the reference, like, okay, how long it is. Now, if this is an older programming language, it doesn't.
So it's in Z. Like the
Yeah, it would be stored. Well, I don't know if it's stored in Z. It might be stored along with the list.
like at the end of the list.
Somewhere with it, yeah. The problem is so in more modern languages, it doesn't work quite like this, but it pretends it works like this. So it's hard to draw that comparison. If you go to like an older language like C, it doesn't know how long it is. In C, if you make an array of index like with 10 values in it, and then you try to index that array at location 100, C will be like, okay. And then you start screwing up RAM real bad. Maybe this. Give me a moment here. Perfect. Okay, look. I'm going to give you a glimpse into something here. So I know you don't know what this means. Ignore it. But I just created something similar to a list. Okay? And I printed it out. And it's just telling me a bunch of nonsense. But what it included in that nonsense is a value that we can effectively think of as the memory location of where it is in the computer. All right? The OX means it's a hexadecimal number, so it's got A's and B's in it and whatnot. But at the end of the day, this is just a number. So it's that memory address 7E291E52E680. Okay? Okay? If I were to go along and say something like B equals A, like I did up here, okay? And I hit run. Oops. And I print out A and I print out B, you will see that they are both in memory location 7E291E0E4460. They are both in the same location. Why? Because they're both literally the one single exact thing being referenced by two references. Okay? I can go and make an actual new thing, just like I'm going to go up here and say ZX equals some new list. Or no, here, let's do it like this. See now, Z is the list A, B, C, D, E, F, G, H. W is the list A, B, C, D, E, F, G, H. But as you can see in this code, how many lists did I create? 2. Each with their own reference. They each have their own single reference. So when I go and modify W at index 4 to P, I print out W and Z, we can see only the one referenced by W was changed. They are different ones. And to carry this like parallel down to here, if I were to go not make a copy of the reference, but make a whole new testing thing and print it out, we will see that they are now, in this case, they are actually like at 2 different memory addresses. One's at blah, 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 4A60. The other one's at 7AC0. Like they are 2 different separate things in 2 different memory locations. I'm trying to, can I do like, how do I do this? Hash of Z? Yeah, okay. Anyways. Yes?
Would it store the 2 lists in 2 separate locations completely, or because they're the same variables, would it reference the same?
They would be 2 separate, they would, don't make it more complicated than it needs to be. They are 2 separate things entirely. There's, in general, in all the programming languages, they are always going to be stored separate. Even if they're the same, you might be like, oh, to save space. No, space is cheap. We don't need to worry about that. But there is a funny exception in the programming language Java with something called like string pooling, where strings will do something like that. And it makes everyone angry. And whether or not Java ought to do it is a whole other thing. But there is one exception. So your brain's in the right space, although, you could try to save some, but no.
I was thinking because we don't usually use the same variable multiple times, multiple things.
You mean the same value?
Yeah.
Well, we're going to be.
No, I know what you mean now.
So if you were here and you were like, okay, I screwed up, but I really did want to make a copy of this thing. I really wanted a copy of that list. Well, we have lots of ways we can do that. One of which is some of the built-in methods that we have to do it. One is literally a method, copy. Now they are different. I said z.copy. I said, hey, Z, make a copy of yourself. It returned a new copy of itself. We had two separate lists. I never actually said, Z, make a copy of yourself. What I really said was, hey, Z, the list that you reference, go make a copy of yourself. So as mentioned earlier, so this goes to what you asked about, like, well, what if you stored like a string in there? As mentioned earlier, in reality, Python will not actually store the contents of the list within the block of memory allocated for the list. Instead, Python stores the contents of their own memory locations, and the list stores references to those contents. So really, it would look something more like that. But that doesn't really matter, okay? That's not important for conceptualizing what's going on. This will throw you off if you weren't paying attention. Yeah? Yeah, it makes an entire new copy. It's entirely separate and independent. There are other ways to do it. You can cheese it a little bit with Python. In Python, you can make a copy easily by slicing your whole list like this. That will also work. But another way to do it is like, look, with lists, there's built-in things. But there's a lot of things that we're going to be making as we go forward with no necessary built-in copy function or methods existing for it. So we might have to write our own methods to make a copy of those things. Which, if it sounds daunting, just think of how you would do it, right? You just create a new empty list and then loop over each thing and make a copy of each thing. Like, it's not that bad. If I go back and show you, okay, A equals 0, 1, 2, 3. So what is A? Someone yell out the answer. What's A? It's a reference to the list. So it's like a list, right? No. It's a reference to a list. Entirely different. By the way, assignment 3, this is going to mess you up if you're not paying attention. If you're not like, oh, okay, I get it, you're screwed for assignment 3. And after assignment 3, you'll get it. You're going to get it. When I do something like this, what am I appending to A? A reference to a list. That's what this was. A was some reference to the list 0, 1, 2, right? No, there's a 3 in there. 3. So when I say A dot append A, I'm not appending this. I'm appending this. So it becomes 0, 1, 2, 3. And A is still referencing this. We've effectively given the list an alias to itself, which is interesting. But that's why this is fine. Yeah?
Can we append A.copy?
Sure. Let's see what happens. What do you think will happen?
Well, it'll just literally put the list in the list.
Yeah. This is not as fun, though, is it?
No.
This is far more interesting because we've given the thing a reference back to itself. So that's what it is. And you can index any variable that references a list. Yes?
What would happen if instead of appending A, say you append 4, number 4, would
So if you're thinking back to that memory picture, this is where we can't go back to that picture of memory that I have to show like, oh, did we just insert the letter A below it? No, because that's really, here's what, okay. I don't know if I should show you, so here's the problem. I don't know if I should show you more how Python actually does it, because in doing so, it might just confuse you from how Python is pretending it does it. How Python pretends it does it at this stage is far more important to understand than how Python really does it. So I'm very cautious. So I'll show you, but just beware that what I'm about to show you is not critically important right now. What's important is you understand what I just showed you. Really what's being stored is A, think of RAM, right? Here's RAM, giant chunks of whatever. Really what A is referencing is this giant thing we call like an object, all right? And this object is this just giant blob of information. For a list, it's going to have information like, I don't know, its size, probably like the series. It's probably going to have a reference to a list somewhere that contains references to the data inside of it. And then if we need a new thing, like if we try to append to it and there's some room, we can add it there. If it's not, we need to make a copy. And there's going to be a lot of stuff going on under the hood for a list. That's the type of stuff we're going to learn next semester. This semester, just think about it like this. Because this is how it's pretending to act. Other questions? It's a good question. You're asking a really good question, but I'm cautious about getting too far in the weeds on that right now. Other questions or anything? Deep copies. Very good timing to bring this up. Why do you ask that question? Oh, okay. Well, let's cover it real quick. So, if I have A equals I'm trying to think the best way to show this. Okay. Let's say I have a list, A. I'm reusing A a lot, but that's fine. For those of you at the back, can you see that A? Good. And that's a reference to a list of some contents. Now, if this list is something like A, B, yeah, I shouldn't, eh? Yeah. 0, 5, 14, whatever. And I say, go make a copy of this, go make a copy of it, right? But what if the contents of this is a bunch of more lists? Which of course is not actually possible. Really what it would be is a bunch of references to other lists. So what if this is a reference to the list 7, 9, 2, another list 2, 4, 6, 1, right? Now if I say, go make a copy of A, not a copy of the reference A, but go make a copy of this list. Oh, what do I mean? Do I want to do this? Make a copy over here. This is. Do I have another? I don't. You do? What color you got? I keep losing them. I leave them in rooms. Oh. The lighting. If I made a copy, I'm going to draw the copy. This is the outside list. If I make a copy of the list that A references, what do I really want? Do I want, because what is this? It's a reference to that list. So do I want a copy of that reference? Or do I want, that would be an example of a shallow copy. A deep copy would mean, well, how deep you want to go. Because this could be a list of lists, or really a list of references to lists that are references to lists that are references. So that we could be going quite deep. So a deep copy would be like, okay, go here and make a copy of, like, I want like a bona fide, real copy of everything in here. So that's the difference. Now, if we're dealing with, here you go. If we're dealing with things that are mutable, like lists, as you can imagine, this becomes a goddamn nightmare. Because if I go and if I thought I made, this is going to be a goddamn nightmare. Okay? Entirely doable, you can work it out, but you're going to be very pissed off the whole time. Okay? There's just way too much. Okay, God damn it. But if everything is immutable, meaning you can't go in and change it, then who the hell cares? I have a deep copy, I have a shallow copy. I don't give a shit. It doesn't matter. It's just data. No one can go in and modify it. Then I have an issue with aliases, one not being updated and the other one. There's no problem. One of the many, 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 many reasons why we love immutable data. Unfortunately, lists are intrinsically mutable in Python. So that's to answer your question about deep copy, shallow copy. Did that answer it? Yeah? Cool. So that's fun. Any other questions about what we talked about or what we just talked about? That right there, the whole mutable nature. Yeah, have fun with assignment 3. Did anyone hear about assignment 3 before they took this class? It's kind of infamous. So, yeah, it's easy peasy tic-tac-toe. Yeah, you're fine. Don't worry about it. You can't wait. It's simple. Other questions or anything before I jump to the next thing? Look, I just put a lot of talk into how this could be complex. It's not if you're paying attention. It gets complex when you try to connect dots and make things more complicated than they are. Slow down. Be a stupid programmer. That's the best way to be successful here, okay? Don't overdo it. You have a question? No? And like I was saying, y'all did pretty well on the first test. Don't let that give you a false sense of like, oh, I guess I'm really good at this. Well, I mean, maybe. We'll see. But if you follow all the rules we've seen, I've given you all the tools, nothing I'm going to give you is ever going to be a trick question. I've told you all of the rules. If you follow the rules, you're going to be fine. You don't, there's no trick questions along the way. Okay? But I know you can do it. You're all a clever bunch. All right. Yeah. Last chance for questions before I go on. All right. Aliases and list trivia. So now I'm just going to blitz a bunch of notes and stuff for you. So A equals 5, B equals A, print out A and B, we get 5, 5. Print out, I modify B, because this shouldn't throw you off, right? A is 5, B is the copy the contents of A. Well, what is it? The number 5. Okay, great, 5, 5. So what's stored in A? 5. What's stored in B? 5. B equals 7. Okay, what's stored in A? 5. What's stored in B? Well, it's 7 now. They're entirely separate. So when I print it out again, we get 5, 7. But with lists, what's stored in A? A reference. What's stored in B? A reference to the same thing A references. So when I modify, Yes, but look. Yes, yes, this is important. Does this make sense? I never modified the thing B referenced. I just replaced what was in B with a reference to a whole other new list. That's fine. But if I were to do this, go in and say, hey, B, go to index 1 of that thing you reference and screw around with it, well, yeah, now we're going to be messed up. Yeah? Yeah? Yeah, this should make sense. Remember, A and B are both referencing the same thing. They're aliases. There's only one list. All right? Yeah. So like, let me show you something here real quick. If I were to say, I want to make like a 3x3 grid, let's say, real quick. A equals that, and say A dot append. No, here's what we're going to do. B, row equals, and then board dot append row. My goodness. All right, okay, I go down here, print board. So we see a list of 3 lists, right? Which we could think of, try to like stack them. Now I have like a 3x3 like matrix. Okay? Sure, it's a list, it's a list, it's a list, but you can think of them stacked. Pardon? Well, yeah, I guess I can do like 0. There, you can think of it kind of like that, right? I just printed out each individual thing. However, what is really stored in board? How many lists exist right there? 4, 1, which is it? Neither are correct. 2. What are the 2? The empty one that we're appending to. So what am I actually appending to board? Nope. No. Equals. Yeah. I only wanted to change the top left one, 0, 0. But I changed all 3. Yeah. And if this is unclear, you're thinking too hard. What did I append? I appended I had something like row 0, 0, 0. In fact, let me make this worse. Let me make this worse by going here and being like, okay, row. I didn't modify board at all, but I did. Indirectly. Because when I had board, ended up being a reference to a list that contained a reference to that list, another reference to the exact same list, and another reference to the exact same list. So when I modified this list, it appears like I have 3 modified lists, but it's really just the same list over and over and over again. Yeah. Careful. We'll end there. Have fun. Have a great weekend. And I'll see some of you later today.